Hi, welcome to Lecture 1, Part 1 of Introduction to Empirical Methods from the Ralph Bunche Summer Institute. So as you can see from the title slide right here, Lecture 1 deals with really weighty, large topics like what is science, and is political science a science, and why is it a science? Theory, what's a theory? How does theory structure our understanding of the world around us? How do we test our theories? And causation, how do we determine when something causes something else? Because this causality is at the heart of the scientific endeavor, because we're trying to understand how some A, right, causes some B. That's true both abstractly, in the sense that we're trying to understand how the world works, but also practically, when we're trying to understand how policies have positive effects or negative effects, we need to understand how the policy, which is A, affects some outcome, which is B. So these are the big topics. In terms of what we're going to see in this lecture, there'll be a lot less math than you might have expected coming into this course, because the fact is, if you don't understand the underlying logic of science and hypothesis testing and theoretical development and causality, then you can do all the stats you want, but you're going to end up with a bunch of results you're not really sure mean anything. So we're going to focus primarily here for the first lecture on these sorts of big ideas. This particular module is focused on the question of science, right? The science of politics. So I say these slides are on the website for the course, so you can see them obviously in the video, but you can also follow along if you want on your own and look through the slides by themselves. I will try to keep reasonably close to the slide just because it's helpful to keep things clear, but I might deviate here and there, but you have the slides as well. Okay. So what's the science in political science is the question here, right? Why is political science a science? Why do we stick the word science in the title of political science? Opening ourselves up to all sorts of snarky comments about, if a topic is a science, there should another word science in it or whatever. But the fact is, political science is a science, and it's intended to be a science. We try very hard to make it a science by and large. And what makes it a science here is the drive to causal inference, right? To understanding the causal relationships between two or more things. When I say causal, I mean that some A causes some B. I would not mean, I'll be very clear about this, I would never mean that A always causes B. That kind of deterministic behavior, as we'll see, is not very much associated with political science or really any social science. Instead, we're going to talk about probabilities and how some A might lead to B happening more often or less often than it would have happened had not A occurred. And that's a little tricky, that kind of counterfactual. We'll discuss in great detail over the next bunch of modules, but that's what we're talking about here. Okay. So the big distinction here is causal inference, trying to understand causality, versus description, the kind of thing you see all the time, and we all do all the time, trying to describe the world around us. That's extremely important. It's vital for everything else we do, description is, and we'll discuss it some today and also for the rest of this lecture. But description at the heart is not really science, right? We're not trying to just tell us how the world looks to us. We're trying to understand how the world works at a deeper level. And that's important, as I said at the opening. It's important not just because of trying to do science, but for practical purposes. We're trying to understand how, say, policies work. In the real world, policies work. They're enacted, and then something happens after the policy is enacted. We want to understand why, right? And if we understand why the policy has the effect it does, we can change the policies to make them work better, right? Because at the heart of this, many of us get into political science not just to understand sort of abstractly how the world works, or the political world works, but also to improve on the policies and the institutions and the political behavior that we have to make for a better world. And that requires a deep understanding of how each of these policies works, not just looking at it, observing, I saw this one work this way this one time, but more generally how policies work at a level that we can repeat and check to see if it's working the same way every time. And then once we know that, we can start varying policies to get outcomes we like better. So any kind of policy implication requires at its heart a causal explanation, understanding of how the policy affects outcomes. Okay, so let's start talking about what they call epistemology here. In general, it's the question of how do we know things? And why is a scientific approach, though, different than other ways that we could know things? Well, traditionally, there are a lot of ways we know things, right? One of the very first ways you experience is authority, right? Your parents tell you this is true, this is not true, and you believe them because they're your parents and you're like two, right? So that's one of the, and that's not just parents, right? That's many examples you can have in the real world in which individuals rely upon authority to make statements, and people take those statements as true due to authority. You can see that all the time, not just from familiar relationships, but from everything from those up to like major political figures who make statements, and individuals believe them just because of the authority invested in the position. So if that's authority, very similar are things like tradition or precedent, right? What happened before is why we should do things now, right? Because it worked before, we can keep doing those things now. Mutual agreement is a little less hierarchical in the sense that if we all tend to agree that this is the way things should be done, then we can keep doing them that way, right? So this is, again, this is a sort of collective belief that helps guide our future behavior. Intuition. That's a little different. Rather than relying upon other people, as the first three examples here did, intuition is about your gut, right? What do you think is the right thing to do, right? All of us rely heavily on our intuition, and in general, intuition is not bad, right? Having built up over the course of years and years experiences in the real world, our intuition is sort of a distillation of all the experiences we have. Now, as we'll talk about, it doesn't always produce the right outcome, the sort of the correct outcome, but it gives us a sort of, as a first pass, reasonable responses to a lot of things. So we often rely upon that as a way to know stuff. It just feels right. Common sense is kind of similar, but it's kind of a codified intuition, right? So, it's just common sense. We all sort of know that this is the right thing to do. Ignoring the fact that common sense became common sense by a long process of individuals coming to that joint belief, and it might not be the right one. So those are sort of common ways. We're going to focus on the last one, though, observation or empirics, right? We're going to try to observe the world and take data, empirical data, on how the world works, and use those data to understand if our theories are correct, or at least if our theories aren't wrong, more precisely. Right. So what are the benefits of this? Well, the benefits of observation are myriad. There are a lot of benefits of observation. These are three of the more important ones, as we'll discuss. One is that observation allows for verifiable and repeatable knowledge. And that's really important. Think about the other ones we did in the previous slide, right? So authority, right? I can repeat that in the sense that if you have authority and you say the same thing every time, I get repeatability, right? But in general, my intuition might change from day to day. If I go to different authority figures, they might have different opinions. Traditions might vary via region or culture. All these things might not be the same all the time. Whereas if I run an experiment and I take data on that experiment and I tell you exactly how I did the experiment, you could, in theory, repeat my experiment and get either the same or different results, right? So you can verify if my experiment does in fact produce the results that you need. So that's important. Falsification is important. Falsification is the ability to tell me I am wrong. That is vital. Science runs completely on producing ideas and theories that you then knock down, right? Being knocked down in science here is not a bad thing. It means that you've tried something and you've furthered our knowledge because someone's come along and said, you know what you said? That's wrong. It's incorrect. That helps us learn about how the world works because we now know how it does not work. And that's really important. And that's how a lot of science works. And it's vitally important that our theories be falsifiable, that we don't just say things that we can't tell are true or not, right? Like, ice cream is good. That's a great statement. I do, in fact, like ice cream. Many people do. But what does good mean in this context? Can I falsify that claim? Right? It's kind of a normative claim. It's a claim about the underlying virtue of something, ice cream in this case, right? democracy is good, right? Again, it's a normative claim. I'm not telling you like how to falsify that, right? How would I falsify that? You could say like, well, it's not good for these reasons. It's not very healthy for you, whatever, if you eat too much of it. That's fine. Maybe my definition of good has nothing to do with health and just how I feel when I eat it, right? It tastes good. So falsifiability is important because without that, we can all disagree. We don't have any kind of joint agreement over time. We could all wonder, what is the truth here? Falsifiability allows you to say with some certainty, no, that's wrong. Right? I maybe can't tell you that's definitely correct, but I can tell you it's wrong, right? It's easier sometimes to go back to examples from, say, like physics, than the more fuzzy examples we'll deal with in political science. But if I drop a ball and you tell me that ball won't fall, and it falls, I can tell you you're wrong, right? I can tell you that because your statement that ball won't fall is falsifiable. I can drop a ball and show you if it works or not. And I can repeat that experiment of dropping a ball over and over and over again and verify that works, that the ball does in fact drop due to gravity. So that's really important. Lastly, and this is the more complex one for people who haven't had a lot of science before, is that our claims, or social science before in particular, is that our claims are going to be probabilistic. By looking and taking a lot of data about how the world works, we're going to be able to make probabilistic claims. What that means is we're going to make claims that say, when I do something, when I enact this policy, this outcome becomes more likely to happen. So we want things like, okay, if I enact this anti-poverty policy, the poverty rate will, on average, be reduced. Maybe in certain cases, there'll be some particular factor that won't make it reduced. Maybe some cases, random luck won't make it reduced. But the claim says, on average, poverty will be reduced if I enact this anti-poverty policy. And that's what we're going for. By taking a lot of data, we can make these probabilistic claims. Okay, so let's start by defining here political science. What is political science? Well, we're going to define it as a study of politics based on a combination of theory and observation, right? And usually the way this works is there's kind of an inductive and deductive step. So what usually happens is you look around, you observe how the world works, right? You notice certain things about the world. So in this case, the example we have here is that individuals with more years of formal education, right, might turn out to vote more often than those with fewer years of formal education. Right? So maybe there's an observation you saw in the world. So you think, okay, I want to generalize from this observation. What am I going to do? Well, maybe I'm going to generalize to the idea that education increases one's propensity to turn out to vote overall. So I'm making a broader claim about how the world works beyond my observation. And that's kind of what we call inductive. I'm looking at data, I'm looking at observation about how the world seems to be to me, and I'm creating a theory from that. What I would then do is try to test my theory on data beyond the data I used to make my theory, right? So if I got my observation from observing friends and family members, right, and acquaintances over the years, I might then go test that claim I'm making, that theory about education's effect on turnout, by taking a large data set on many people whom I do not know, and then test my generalization, right? So that's what we're doing really. We're observing, we're creating more general theories, and we're testing them on larger data sets, on different data sets. And the goal of this is going to be what we call inference. Inference is, as it is in English, the ability to infer something from something else. So there's really two kinds of inference we're going to deal with here. One kind is causal. That's the scientific kind we really care about a lot in this class and overall in political science. We're going to try to infer and guess, basically the best we can, about an unknown causal relationship between two or more variables. So again, some A might cause some B. So that's a causal inference. Now we'll get a bunch of data that won't necessarily tell us that's true for certain, but we'll try to infer from our data that A does in fact cause B. So it's our best guess about some unknown given known information. Second is going to be descriptive inference, and this is going to be less of a scientific endeavor, but still very important. I don't mean at all to be diminishing the importance of descriptive inference. It's just different from some of the scientific endeavor we're talking about here. Descriptive inference is trying to infer an unknown fact about a single variable. So, for instance, if I want to know the presidential approval rating of the whole country, I'm not in general going to go out and measure everyone's approval for the whole country. It's extremely costly and time consuming. So I sample the population. I maybe take 1,000 people or fewer or more, and then I measure their average participation. Their average level of support for, say, the president, and then I use that to infer how the population as a whole thinks about the president. Right? That's descriptive inference. I'm trying to describe people's opinions about the president, not trying to set up any causal relationship, just describe how people feel, and I'm going to infer that feeling from a smaller sample of individuals. That's descriptive inference. Inference, and this is super important, inference by definition is uncertain. It involves error. There's literally nothing we are going to do in this class, and nothing political scientists do ever, in which you can say, oh, A always causes B, guaranteed, no problem. We can't even say, oh, A always leads to like a 50% chance of increasing B. Everything we say fundamentally involves error. And honestly, that's true for all sciences, even though it's kind of hidden often. It's just that in a science like physics, the error is very, very, very tiny. Through years and centuries, in some cases of experiments, the error gets smaller and smaller and smaller. In political science, it's a relatively new field. The data are much fuzzier. The problems are frankly harder to figure out, and the errors are much, much bigger. So that causes error. So we're always going to have error. That does not mean this is worth it, right? Just because I can't say with certainty what's going to happen, it does not mean my knowledge of what might happen with error does not improve over just random guessing, right? So learning about how the world works, even probabilistically, even with error, can help us understand how policies work and help us predict outcomes from political interactions. That's important. There will be error. That does not mean it's worth this. It also is important because it is a human characteristic that when we see things that have some probability attached to them, we immediately split it to like 0 or 1, right? Guaranteed or never happening. And that's just not the case. That's an important, difficult thing to get over, but it's important to get over it because it tends to bias our thinking, right? Understanding that the world works with some probabilities and it's not all guaranteed or never happening is an important first step to sort of thinking more scientifically. Okay, so let's turn to causal inference now. As I said, causal inference is inferring a causal relationship, so inferring some A causing some B via data. We never ever observe this. You have never observed this causality ever either. No one ever has, right? Even when I take a ball and I drop it, I say, oh, well, gravity clearly causes it to fall. We don't know that for sure, right? We know that we have a bunch of theories, and it seems that those theories are consistent with a causal explanation for why that ball falls based on gravity. But it's always possible that there's some crazy, wacky theory you've never thought of before that's the actual truth, and it's just that it seems the same in whatever like setting we're looking at to the gravity explanation. That's always possible, right? We could do an incredibly amazing experiment where we have a policy and we have some outcome and we just implement that policy and measure really, really well how it works and say, it definitely has that effect. But the fact is, at the end of the day, we just can't be sure with 100% certainty, right? We don't know if every possible reason that policy might have worked has been taken into account. Maybe that policy only worked because one single individual named Alice happened to be there that one day, right? We don't know. And because of that, we can never be sure of anything. However, our goal here is to get closer to being sure, right? To improve our beliefs and increase the belief that some A causes some B, and thereby increase sort of the scope of our knowledge. Okay. To get causation, right, there's a bunch of stuff that are needed. One involves correlation. So a correlation is when the values of two or more variables tend to move together. So let's say I have an A and a B. Moving together might mean whenever I increase A, B tends to increase too. Or it could mean whenever I increase A, B tends to decrease. These are all fine. They're correlations. They're variables moving together, and they're sort of first step, right? If I drop the ball and the ball doesn't fall, right, then I don't have any kind of correlation between my action of dropping and the behavior I'm trying to show, right? There's no correlation at all. If A causes B, then it better be the case that when I do A, B happens more often. Otherwise, I'm not even getting a possibility of a causal relationship. So correlation sort of precedes, logically, causation. It's necessary for causation to be true. So a valid causal inference requires that the theory says X should cause Y, right? Gravity should pull that ball down to the ground. And second, we have evidence that, in fact, when X happens, Y happens more often as well. So if the theory is that gravity pulls the ball to the ground, when I drop the ball, I should see the ball falling to the ground more often than it did before. So the first one's a theory. I have a theory about how things should be related causally. And the second one's correlation. I see two things that vary together. And by the way, this is a good time to stop for a moment and just point out this is pretty fast because it's super awkward to stop in the middle and just wait in front of a webcam the way you would in class to sort of see if everyone's on the same page. You should feel free at all times to pause, stop, think about it for a while, take a break, come back, rewind, whatever. That's one benefit of this kind of setting. So even if I'm talking kind of fast, I'll try to say the words more slowly. I do tend to talk too fast. However, it's important to stop frequently and make sure you're sort of keeping up with all these things, because some of these concepts do get kind of thorny and they build on each other. So if you think, okay, well, I didn't quite get this, but I'm going to go on anyway, don't. I highly advise you stop. Make sure you get that before going on, and that'll make everything else afterward much easier. Okay, back to the slide. So we're going to infer causal relationships when we have a theory that says X should affect Y, A should affect B, and we see evidence that A and B are related. So empirically, so they happen together more often than not. Or X and Y are related together more often than not. But again, all these inferences we make about causality are fundamentally uncertain. We're never exactly sure that A causes B, that X causes Y. All we know is it seems to be consistent with our existing theories. And we'll get into more of that in a second. Okay, so but we could use a couple more definitions to make things a little clearer. So again, correlation means the values of two variables tend to move together. So when X gets bigger, Y more often gets bigger, right? Or when X gets bigger, Y more often gets smaller, right? These are all correlations. Causation, the third bullet point here, is when the change in the value of some concept tends to produce change in the value of another concept. There are many situations in which you can have a correlation between two things, but there is no actual cause between those two things, right? We can see all sorts of stuff that could happen that might just happen due to chance and be correlated in some fashion that might not mean anything. And we'll go into a lot of detail on that over the course of lecture 1. So importantly, causation, right? X causes Y, does imply correlation. X and Y move together, because if X causes Y, then it must be the case that X and Y move together, right? How else could it be? If X causes Y and they didn't move together, then X wasn't doing anything to Y, but then X couldn't be causing Y. So if X causes Y, if changing X changes Y, then when I change X, Y has to change, right? It's sort of implicit in the definition of causality, right? If X changes Y, then when I see a change in X, I should also see a change in Y. But the same is not true in reverse. Just because X and Y are correlated does not mean that X caused Y. Just because I see X move with Y doesn't mean that X caused it. Something else might have caused it. maybe a third thing caused both X and Y. And we'll get into that particular example of spurious causation pretty soon. Okay. Those are 3 of the bullet points here. The fourth one I didn't mention yet is prediction. Prediction is a tricky one because prediction is historically underused in political science. We tend to think about understanding, explanation, and shy away a little from prediction. And that's, in my opinion, a bit of a mistake because prediction is central to the scientific endeavor. And it's also central to all the stuff you see data scientists using data for, right? When Facebook and Google and Twitter and Instagram and every social media platform, when Amazon or any or Walmart or Target or any store and any marketplace takes data on you, they're taking a lot of data and they're trying to use that data to predict what you will do, right? That's the goal of all this. It happens in the political realm too, right? All these newer data centers are taking tons of data on you and your interaction with the political sphere and putting it together and trying to predict how you will vote. And then try to identify who's likely to vote for particular candidates and then ask them for money to help them win over other people. So this prediction is basically knowing the value of some X, one or more variables, can help you predict the future value of some other variable Y. Prediction is very closely associated with correlation. If X and Y move together, then if I change X, I should be able to predict how Y is going to change. Right? If X and Y are correlated and I change X, that should help me understand how Y changes. So that's correlation. That's prediction. And prediction and correlation are closely attached. Okay, so this one over here is causation in 2 different ways. Deterministic versus probabilistic causation. I said before, we don't ever say really that X always causes Y, right? Determinism is when you know definitely something will happen, right? So if I have an X, I'll always get a Y, right? In some senses, I can't get the Y without the X, right? The X causes the Y. That's not quite true. I should be more careful there. X causes Y. That's the deterministic relationship. This can be relations over individuals or states or countries. Involves variation. So when I vary X, Y varies too. It can be quantitative or qualitative. It could be with numbers, or it could be just verbal with words, thoughts. It doesn't really matter. The upshot is the deterministic relationship means it always happens. We think in general things like gravity, the ball falling again, right, is deterministic. If I drop this ball, I can tell you to very high accuracy how fast it's going to be moving when it hits the ground. All you got to tell me is what planet I'm on, how high up I am, and distance between the ball and the ground. And I can tell you how fast that ball is going to be moving when it hits the ground. I can tell you how long it would take to hit the ground. All sorts of deterministic relationships, right? If I'm playing pool and I hit the pool ball, I should be able to tell you with pretty exact accuracy where the balls are going to go. I might get complicated, but I can tell you that these are close to deterministic relationships. A probabilistic relationship, in contrast, is different. The cause X is usually present when the outcome occurs. In general, a probabilistic relationship has X's presence changing the likelihood that Y happens, but not guaranteeing that Y happens. So there's a difference between sort of biasing the odds of something and guaranteeing the odds of something. Think about if you're playing, say you're rolling a fair 6-sided die, right? And now I bias one of the sides a little bit, and that increases the chance that a 6 pops up, right? But I still get other numbers. That's the kind of thing we think about for a probabilistic causal relation, right? So we might say this policy, right, when it's enacted, increases good outcomes, right? Increases the chance that, say, poverty decreases. But still things could happen that aren't that. It still could be the case that we enact the policy and bad things happen. It's not guaranteed. In contrast, if we had a die that was just weighted tons on one side and always rolled a 6, in that case, it's deterministic. It always rolls a 6. There's no uncertainty. If I have this die, it'll roll a 6. That's different. In general, political science only deals with probabilistic causal relationships. We do not try to do deterministic relationships. Whether or not you think that they're possible or not is up to your own personal beliefs, but we don't try to do that in general. We try to only produce and assess probabilistic causal relationships. We try to understand when some policy or some factor X leads to Y happening more or less often. Okay, so now I want to go into a little more detail on some of these things. Descriptive inference, and this will be one of the longer modules, by the way, because it covers a lot of opening ground. I mentioned there's two kinds of inference: causal inference and descriptive inference. Descriptive inference helps us understand how the world is right now. It doesn't provide connections between two things via causality. It just tells us what the world looks like now. So it provides us a profile of interest. For instance, it tells us, what the unit of interest is, how it varies. It gives us judgments, both qualitative and quantitative, about it. And the inference part is trying to infer the characteristics of a population from those of a sample. So say we measure, as I said before, we measure the beliefs on some survey of 1,000 people, and we infer the beliefs of the entire population from the 1,000 people we sampled. As we'll see later, that requires our sample be random and a few other things, but we're trying to infer characteristics of a population from a sample. That's inference. If all we care about is a single property of that population, that's descriptive inference. We're trying to describe that particular part of the population, that particular characteristic of the population, by inferring from some subpopulation, some sample. Description is really important. Without description, we can get nowhere else, right? We need to know how the world looks in order to take data on it, understand any kind of causality. But descriptive inference is not our goal, right? We're not satisfied by just understanding how the world looks at the moment. We want to know how it works fundamentally and how all the little pieces of it are connected to each other causally, how each X changes each Y. That's our goal. And again, I really mean, I'm not just saying this, descriptive inference is very, very important. It's just not the goal overall of science. It's the goal of other really important things, but not science in this case. Causal inference, which is also important, is the goal here, to understand how X causes Y. Right. Now, this slide is one that might not be as obvious why it's here, unless you spent time looking at data science already. Now, data scientists do a lot of the things we've been talking about. They take data on how the world works and how samples of the world work and try to infer causality from those samples. What is often missing, however, is some theoretical connection, some theoretical backing that explains why A should cause B, right? So instead what we see is that in this big data set, A seems to cause B because they have a very strong correlation, and you've controlled for a bunch of other things that could have maybe caused B instead. We'll get to what that means later. The thing is, that's insufficient. It's inadequate for real causal inference for several reasons. One is we never know if our observations are inaccurate or biased. They often are, right? When we take data, it's never the perfect data we could possibly get, right? It's not a perfectly representative sample of everyone who could ever have existed in the world with all their varied personality traits and quirks and characteristics, right? It's a particular sample of individuals who chose to participate in some data gathering process for a particular reason, right? The people who shop on Amazon are not necessarily representative of the entire population, so data on their purchasing behavior does not necessarily tell us about everything. The people who fill out surveys doesn't necessarily the same people who might vote in an election, right? We might not have perfect observations about how the world works just from the observations themselves. Because we don't have information about everyone, right, we might overgeneralize from our inaccurate observations and come up with theories or claims that don't necessarily apply to everyone, but only to a particular subset, right? We might selectively observe phenomena of interest to us and gloss over the stuff we don't care as much about or that don't fit with our worldview, right? This is a very common psychological factor. All human beings, when seeing new information, tend to try to structure it and take it in the framework that we're familiar with, right? We don't say, oh, that's new. I'm going to create an entirely new way of looking at the world so I understand that, right? Instead, we have our way of looking at the world and we say, oh, that clearly fits in this way. So what we do effectively is take the new information, kind of smooth out the edges, and fit it into our existing sort of structures or worldviews, right? The problem with that from a scientific perspective is that we're not really getting all the information, right? We're getting unbiased information. We're getting selective information. We're taking the stuff that best fits our worldview and discarding the stuff that least fits it, which is guaranteed to sort of reinforce our worldview, not guaranteed, but likely to reinforce our worldview and be less falsifiable, right? Let us have less of a chance of actually changing our worldview, which is important. It also can lead to illogical reasoning, right? So maybe we get two different outcomes in some big data set, and we think, oh, they both must be true. But then we discover they're kind of contradictory in some fashion, right? Well, we might then reason through and say, oh, well, it's really contradictory, but there must be some complicated reasoning of why they both could exist at once. But in reality, if we had a theory, we might really question why they both existed at once and maybe try to understand how one of them might be biased, maybe both. So in general, we're going to really highlight in this class that to draw a valid causal inference, you need both logical support, theoretical backing, right, a reason why things might be true, and also empirical support. Okay. So to do this, we're going to use the scientific method. And this is the same scientific method that all scientists use for hundreds of years. It's not different. The idea is we're trying to produce evidence to see if the relevant data that we observe are consistent with some expectations of a theory we develop, right? So we're going to use that. That's the evidence part. And the reason part is we're going to try to put together hypotheses from the theory to see if they follow from assumptions, right? So we're going to start off with some assumptions of our theory. We're going to derive some hypotheses. Then we're going to take evidence to see if those hypotheses bear out in the real world. And if they do, we'll say, okay, we get some support for our beliefs, right? We're not claiming that scientists can't be emotional or passionate about our work. Of course we are, right? For human beings, we are emotional and passionate about all sorts of stuff, right? But the importance of the scientific method is it allows us to divorce our conclusions from that emotion and passion as much as possible. And then even if our choice of research question and our approach are just completely driven by some emotional response to the work, to the question, we can still produce some measures that are really clearly laid out, and evidence and reasoning that you, who might not share any of my emotional response or any of my passion for the topic, can still take all my reasons and my evidence and judge for yourself how well you believe it. So maybe you see my evidence and my reasoning and say, you know what, I see why you got what you did, but I disagree with some of your assumptions. That's fine. That's great. And that's where things like emotion and passion can come into play, because maybe my assumptions were driven by an emotional response and not the truth. In which case, you can come along and change some assumptions and redo some of the stuff I did and see if you get different conclusions, and then see if your conclusions bear out in the real world more than mine. And that's great. That's the scientific method. That's the progress of science. It's incremental. It builds on itself. Every individual produces something, and someone else builds off of it. And that's great. Even the most famous scientists in the world massively built their conclusions off of others' work. Without that earlier work, they would not have come to the conclusions they did. It's fundamentally important, and having these clear, rational reasons and evidence behind your results, behind your science, is vital for moving forward our understanding of how the world works. If all we do is just launch opinions as in back and forth op-eds, right, we will get nowhere, right? Because you've all read op-eds, right, and one person will say one thing and the other person says the other thing, and they pick and choose what arguments to use based on what they think is most likely to sway your opinion. And it's like a debate, but there's no actual evidence. And, there's selective evidence, but not really deep evidence, and the people can't talk to each other. In contrast, no matter what my political background and no matter what anyone else's political background is, if we're both political scientists, I can lay out my assumptions, I can lay out my reasoning, I can lay out my evidence, and you can judge whether or not you believe it. And the belief is not based on what your political opinion is. It's based on how you interpret my assumptions and my reasoning and my evidence. You can go out and replicate it. You can do things yourself. You can vary assumptions and see if you get different outcomes. And then we can judge which one is likely to be more right based on how well our reasoning and assumptions and evidence match with the real world. Okay, and this mutual agreement on how the world, how science should work, helps us avoid these kind of just purely emotional, purely passionate debates about how things should be and what is true and what isn't true. That could otherwise make it impossible to make forward progress in accumulating knowledge and information. Okay. What do we need for this? Well, we need to analyze the real world, right? We can't analyze fictional, counterfactual worlds. A counterfactual is a kind of weird word. Here, counterfactual means counter to fact, right? So it's an alternative world that you posit, that you put forward, that you imagine in order to compare it to the real world. It's often very useful. We'll get into more detail about that. But when we're trying to understand how politics works, right, we need to understand the real world, right? Analyzing the real world and not some fake world, right? We need to understand concepts, not constructs, right? We need to know, we need to think about democracy and voting rights and public opinion, right? And not things about one particular president or one particular congressperson or one particular country, right? Concepts in general, not proper nouns, not individuals, not even individual countries in general, right? We need to know about how things work at a deeper level. That should apply to all countries with certain characteristics, not just one at this moment in time. And we're going to propose testable causal relationships among concepts. These will be falsifiable. So we'll say, hey, I think policy A should yield outcome B more often. So we can falsify that, because if it didn't yield B more often, then it would be false. It would be false and it would be wrong, and that's fine. So we need a falsifiable causal relationship between concepts, and we need to know what evidence is needed to possibly falsify our hypotheses. So if I say, okay, this policy A causes B more often, I need to tell you as well how you could test that, right? How would I measure A? How would I measure B? And then could you go out and measure it yourself so you could see if A in fact led to B more often or not? See if I was falsified. See if my claim was falsified or not. And again, none of this involves proof, right? We can't prove our theory with the evidence, right? Why not? Because it's logically impossible, right? So let's say our hypothesis is that A causes B, right? And we go and observe B. That's our evidence. Can we then say, oh, clearly A caused B? Well, no. Even though A happened and B happened, right? Maybe something else caused B, right? We don't know, right? We can't be guaranteed to know that. What we can be guaranteed to know is that, say, we say A is going to cause B more often, and then we get really, really strong results that say whenever we have A, we have much, much less B. That's going to falsify potentially our claim, right? Because our claim was that A increased the chance of B, but in reality, all our evidence says A significantly decreases the chance of B. And that's not what we said. So that's going to falsify our claim. But we still can't say, if we did support our claim, if we saw A leading to much more B in general, all we get is support for our beliefs. We wouldn't prove them. We'd say, you know what, everything we've seen so far is entirely consistent with the notion that A causes B. But I can't be sure of that until I have more information, right? So most really good theories of the kind that you are familiar with in everyday life, right, are not just proven by a single test. They're proven by many, many tests of all different angles and all different characteristics of the theory, right? Just recently, in recent years, a 100-year prediction of general relativity was shown to hold, right? Because some of the stuff is really hard to test, like gravity waves. So it took 100 years to get up the technology to test that particular part of the theory. But even then, having shown that seems to be supported, doesn't mean the theory is correct. It just means we have additional support for the theory. And all we can really do is keep building up additional support for the theories and trying over and over again to falsify them, to put more and more pressure on the theory, because the more pressure the theory takes and stands up, the more belief and confidence we can have in the theory itself. So that's what we can do here, right? So if the evidence is consistent with our theory, we infer that our theory isn't wrong, right? We've failed to falsify it. It might not be right, but we have not made it wrong, right? And that's important, right? All we're really doing is providing additional support for our theories, and part of the scientific endeavor is building up multiple sources of support for our theories. Okay, so I'll conclude this module here. A science of politics, right? Despite the fact that you see all over the media and social media and regular media that it's somehow impossible to have a science of politics, that's just flatly false, right? Like everything else in the world, the political and social worlds produce observable phenomena, right? That we can see and measure, and then we can conceptualize them, and we can produce these data, political and social data in the world, right? Given those data, we can then identify patterns in the data. And then we can try, once we have these patterns, to develop causal explanations, theory, about the cause and effect relationships among concepts that lead to these patterns. Right? Once we've done that, we take even more data and try to see if these hypotheses about these patterns actually hold more generally. Right? That's what we do in science, and that's the goal of all this, and that's the goal of the rest of this course, is to build out tools and ideas you need to do this, to develop causal relationships, figure out how to put them in the form that you can test, how to measure the things you can use to test them, and then how to actually do the statistics to assess our test, to see whether or not we have support for our theories or if our theories have been falsified. Okay. So that was a long one. They won't all be this long, but I hope you enjoyed that, and I'll see you at the next module. Thank you.